Hello, welcome to session number 10 in the series Microwave and Millimeter Wave Circuit Design. My name is Anurag Nigam, and in this session I'm going to very quickly design one hybrid 180-degree hybrid or a rat race. So let's get started. So you just create a new schematic and call it hybrid 180. Hybrid 180. Right. Okay, so the next thing what you're going to do is you're going to launch LineCal. So you're going to go here and tools LineCal. Okay, so you start LineCal here. I'm going to make sure I'm recording right. Okay, so in this case you know the substrate is going to be 5.92 and the height of the substrate is going to be 97 micron, 97 micrometer. Right, and the thickness is going to be 9 micron or 9 micrometer, and the conductivity is 6.17. 6.17 is the conductivity, and 10 delta is 0.002, right? And then the frequency is 10 gigahertz. So I want to create a line which is 70.07 or 70.7, sorry, and I want this line to be what you call 360. Right, so 360 is going to be lambda, right? So I want to look at 360. Okay, and I want the answer in microns, and I want, yeah, so I want the answer in microns. I'll say synthesize. So it's 65.5 according to this, and then it's going to be 15 mm, right? Or rather 15,000 micrometer, right? 15,000 micrometer. So let's look at some simple maths. So what we want is, uh, let's do the simple mathematics this way. The width is 65.5, right? So 65.5 and the radius is, so basically if I was to do circumference is of a circle is 2 pi r, right? So 2 pi r is equal to twice of this L. Okay, twice of L is 2 pi r, isn't it? 3 lambda by 4, and the other side is going to be 3 lambda by 4, so that is 6 lambda by 4. Let me see. So let's see this. So what we want is insert shape. So let's just clear this out. Okay, so we want, okay, so we want something which is going to be 3 lambda by 4 this way, right? And then lambda by 4, lambda by 4, and lambda by 4. Again 3 lambda by 4, isn't it? So what it'll do is it'll go lambda by 4, 3 lambda by 4, that is going to be lambda. And then lambda by 4 and lambda by 4, that is going to be lambda by 2. Okay, so this is going to be 3 plus 3, that is going to be 6, isn't it? So let's just do this. Okay, so what we want here is the following. Okay, so we want 2 ports to be around here, right? And okay, so we want 2 ports to be here. Okay, so we want something like this, right? Lambda by 4, lambda by 4, right? Okay, so we have 3 plus 3 6 lambda by 4. 6 lambda by 4 is 3 lambda by 2, right? Okay, 6 lambda by 4, or 1.5 times of lambda. That's what we want. So then the line cal says that this is 15 330. So 3 by 2 of that. Okay, so let's do a calculator. Okay, 15 330 into 1.5, that is 3 by 2. So the total circumference is this divided by 2, okay, divided by pi, right? So that will give you the radius r. Okay, so divided by pi. Where do I see pi? That's horrible. Can't see a pi. There is pi. Is equal to divided by 2 and divided by pi. So that is going to be, so divide by 2, 11, divide by pi, that's 3659 or 3660. So let's write that number. Okay, so the radius is going to be home. Okay, so this radius is going to be 3. Okay, so let's make it so that people can see it. Okay, so this radius I want to be 3660, isn't it? So the calculator says if I take again I'll do the maths. So 15 330 is lambda by 4, is basically lambda 360 degrees lambda, right? So multiplied by, okay, so I want the 6 by 4 of that, right? Multiplied by 6 divided by 4. So that is that. And then I want to divide this by 2 and then divide this by pi. So it's going to be 3660 micron. So this is going to be insert text 3660 micrometer, right? So that's going to be that. Okay, so now I want 65, right? So basically 65.5. So that half of that is on the other side. So 65.5. So I will do plus 65.5, right? Divided by 2. So this will be the outer radius, right? Okay, so that would be, so let me look at the calculator. Plus 65.5 divided by 2 is equal to uh, 3692.5. So this is going to be equal to 3692.5 micrometer. Now these numbers will be slightly different, right? So it doesn't matter. And the next thing is going to be minus. So the inner radius is going to be that number minus this. So let's go back to the calculator and I am going to minus 65.5. So this is going to be equal to 3627. 27.0. Okay, so I have the outer radius, the inner radius, and then if you divide this into 1 2 3 4 5 6 6, so if I divide the angle 360 by 6 is going to be 60 degrees. So the angle subtended, sorry, so the angle subtended by this, right? So the angle subtended by this should be equal to 60 degrees, isn't it? So that way, so we are talking about this angle. Okay, so this angle should be equal to 60 degrees, isn't it? So let's put here 60. Okay, so here it will be 60 degrees. Okay, so this is our layout going to be, isn't it? So I'm going to quickly go ahead and do this layout, right? So we are done with all the maths. So I'm going to go here, and I have already created a 180-degree hybrid. I'm going to create a layout for this. Layout and say create. So first of all, I need a circle, and that too on M7, right? On the M7, I want a circle. So I will put here insert coordinate entry absolute value 0 0 and say OK. So I want a circle with a radius of 3692.5. 3692.5. So insert coordinate entry. So x is 3692.5, correct? And 0. Okay, and say OK. So I want this circle. Then I want another circle which is 3627. 3627. So 3627. So insert coordinate entry 3627 and 0. So that's the other one. So I have 65 here as the 65.5 as the width. So I am going to measure this. Okay, see roughly 65.5. If you want exactly, it should be 65.5, isn't it? So from here to 65.5, right? So you can see this is 65.5. So we are all set. All we have to do is union minus intersection. Select this, and say edit, merge, union minus intersection. Now, I'll tell you one thing. When you do this kind of design, because it's a circular design, so you might have to play with the radius a little. So this is a fast cut design. So the next thing which I want to do is a radial stub. So that's a radial stub. So I want, forget about the width. Width I'll keep as 2 micron, doesn't matter. And the length is the radius, right? So the radius is 3692.5, correct? And the angle is 60 degrees. 60 degrees, right? So if I apply this, it looks like this, right? So I will just mirror this. So I'll mirror this, and I will place it somewhere at the center, right? So I will say insert coordinate entry and say absolute value of 0 0. Say OK. So now you see that this is going to be lambda by 4, and then this is going to be another lambda by 4. So all I need is 50 ohm. So 50 ohm is basically uh, so 50 ohm line, right? So let's do a trace, and I want this to be truncated, and that's fine. And the width is going to be 139 for a 50 ohm line, right? So I'm going to choose a point here, and I am going to go 45 degrees. Now, not 45 degrees, I should go 60 degrees, isn't it? So I will go along this length. Okay, and I want this to be like 120 is okay. 120 is okay. Okay, so I want this piece, correct? So what I'm going to do is I am going to move this piece to the center. Yeah, roughly over here, correct? And I want the same piece on the other side. So I'm going to copy this, reflect it like this. So it's going to be over here. And then I want the same piece, okay, 120. So I'll make another line which is going to start from roughly here. Okay, and I am going to go 120, not 120, half of that. Or let's say I go 120, how does it matter? 110, 115, 120. What? Okay, I'll do that again. So go to the center and go out and go to roughly 120. So I'm not going to spend a lot of time on getting 120. Okay, and I'm going to move this to the inner side somewhere here. And I'm going to make a copy of this and go to the other side, roughly here. Okay, so I'm done with my rat race. So that's a rat race. Okay, that's funny. 1, then I'm going to say 2 and 3 and 4. Okay, somehow I don't like this, right? So it's okay. Let me just do that. Edit, merge, union. Okay, so this is my rat race. And I want a piece of line. Okay, so what I want is a piece of line, which is this much. Let's see. And I'm going to move that over here. And I'm going to rotate this. Okay, somewhere I'm going to put it to the center. So, wrong side. So, the results are going to be slightly different. Okay, I should have done this earlier itself. Anyways, so I want to come out on a straight edge, not on a slanting edge. That's the whole point. So I'm going to merge these also. Edit, merge union, right? And edit, merge union. Okay, so we are fine. Now I need a ground plane. So a ground plane is M6, and I'm going to go from a center to this radius is 3000 something, right? So I want to go on top of that, right? So let's say I want to go from here. So I want to go from here as a square block. So insert coordinate entry. Insert coordinate entry. So I want to go roughly 3692, isn't it? 3900, sorry. 3000, what was the width? So let's say 3900, doesn't matter. And 3900. Say okay. Huh? Okay, just 1 second. What is this 3900, right? Doesn't matter. Okay, so let's do this. Okay, so I've gone this way 3900, isn't it? Okay. So this extent is done. Correct. So this is my ground plane. I'm going to copy that, rotate it out, and I'm going to place it around the center. That's there. Okay. So one more thing I can do is this should be at the center, right? Sorry. Huh. Okay. So now my ground plane should be this. Okay. So I'm going to remove this. So this is my ground plane, and I want to cut a small slots in this, right? So I'm going to cut very small slots. So really doesn't matter because this is a very small discontinuity. So let's copy this slot. So what I'm telling you here is the following, that this is an approximate design. It can be refined, but just 1 second you give me. Okay. So I'll say edit merge union minus intersection. Edit merge union minus intersection. Edit merge union minus intersection. So that's that slot. Edit merge union minus intersection. Okay, so now we have got 4 ports. So I'm going to number it like this: 1, 2, 3, and 4. So if I put power into 1, then 2 and 3 will give you 3 dB power, and the port number 4 will be isolated. So I'm going to go 1, 2, 3, 4. Then I'm going to go 5, 6, 7, 8. Now I'm going to declare them as ground reference, right? So I will go click on 1. So it will be, the ground reference would be 5. Okay, so this is on metal 6. Correct? So this is done. Next is 6. So 6 will be on metal 6. Correct? That's done. Then 7. 7 will be on metal 6. Metal 6. Done. Then 8. 8 will be on metal 6. Done. Okay, so now I'm done. Let me make sure I'm recording. Yes, it is recording. So I got this thing ready. Now I'll go to EM simulation setup, create a setup, and here I'm going to go to ports, layout edit, port editor, sorry. And here 5 is a ground reference for 1. Then 6 is a ground reference for 2. Then 7 is a ground reference for 3. And 8 is a ground reference for 4. So we are done over ground referencing. Next, I'm going to look at the 3DM preview to see if the grounds are connected properly. Okay, so to me, the grounds are connected properly, right? So don't worry about the hexagon stuff, right? So that's okay. Fine. So go to frequency plan, and let's say I want to do this from 9 gigahertz to 10 gigahertz, 11 gigahertz, 50 ohm, and then I'm going to save all the currents for all the frequencies and mesh, edge mesh, transmission line mesh, and model and shore model. I'm going to save this and I'm going to say simulate. So it's going to do the meshing. It has done that. Now it's simulating. Okay, hopefully if we haven't done a blunder, we should have something uh, which would be close to what we want from a rat race. Okay. And if we have done a blunder, I would have to make a new video. So let's see. This problem comes from the curvature part of it, right? So let's go ahead and look at S11, S22, S33, and so on. S11, that's the center, so that's okay. That looks okay. Then let's look at S22, S33, and S44. Okay, so all of them are at the center. So our design was okay. Our design was good actually. Okay, so everything is at the center, and we can put this in a rectangular coordinate also, right? S11, S22, S33, and S44. Okay, so they are better than 18, right? So they are better than 18. So let me change this to this one. So they are better than 18. Now let's look at S21. So S21 in this case is going to be 3 dB down. So S21. Okay, so that's over here. I'll make it green color. Okay, let's put a marker on this at the center. So this is 3.2. On the edges, it is 3.5. Other side is 3.3. So somewhere center, it is around 3.2. So that looks okay. So let's look at S31 in dB. So S31 is this one. This is even better, right? So let's make this one as magenta. Okay, so 31. So let's put a marker on this. Okay, so this is 3.1. So this is 2.9, 2.9, and over here 3.1. So basically the power divides into half. Let's look at their phase. So if I take the phase of S21 and subtract from that the phase of S31, it should be close to 0, right? So I'll say this Control C minus Control V and do a 3, and oh, S21 phase minus S31 phase. Oh, we have an error of a cross frequency error of, so this is over here. So we have a 2 degrees error at 10, and we have 7 degrees error at 9, and minus 7 degrees, and then we have 3.5 degrees error at 11 roughly. So we are close by, doesn't matter. And the next thing I want to look at is the isolation. So on the same graph, I'm going to put S41 dB. So that's S41. So S41 I'll make green color, so that is easily visible. So you see the isolation, the isolated port, which is port 4, is better than 22 dB, correct? So this is the rat race design. And if somebody is interested in current visualization, which I do anyways, so I can go to setup at 10 degrees. At this point, I'm going to put power into port 1, animate it out, and change this to 1 and change this to 3. Look at that. So I'm putting power into port 1, it's dividing into 2 and going into port 2 and port 3. And port 4, it is approaching from two different sides, and as it is the magnitude, it is going to be, both are going to be green, but they are opposite in phase. So they are going to cancel it out. Right, so this is your rat race, right? So let me, okay, so here I'm going to stop session number 10, right, in the series microwave and millimeter wave circuit design. Thanks a lot.